Hello, everyone, and welcome to today's webinar on fast back EMF measurements for end-of-line motor validation. Your microphones will stay muted throughout the session. If you have questions, we will address them at the completion of the presentation using the Q&A feature of WebEx. However, you are welcome to type in questions at any time. Please send the questions to both the host and the presenter so we can respond. Our presenter today is Mitch Marks. Mitch has an MS in electrical engineering from the University of Wisconsin-Madison. He has been at HBM since 2017, where he is the application specialist for electric motor testing. He first worked as a researcher at the university, working with traction motor testing and power grid research. Mitch, it's all yours.
Thanks, Krista. One fun fact is actually my first job as an intern was designing end-of-line test systems for electric machines. They're a little simpler than what I'm going to propose today, but I'll point that out when we get there. So today's topic is back EMF measurements for end-of-line motor validation, and I think this is a good one, so I hope you guys enjoy. Just a quick overview of the agenda today is first and foremost, we're going to introduce back EMF and motor construction and why we want to do these tests, why we care. We'll look a little at position sensors because I think that's one thing that doesn't get looked at as closely when we talk about the back EMF measurements, but I think it's equally as important for an end-of-line scenario. Back EMF testing kind of from a fundamental high level. We'll go through a really nice testing example. We'll look at some successes and some failures. We'll look at a novel method for accelerated back EMF testing. This is some really cool stuff, so I think you guys will enjoy, especially if you've been doing back EMF testing and maybe are looking to spice it up. Cloud storage and custom workflows, these are absolutely relevant topics, especially when we start talking about big data sets and testing lots of pieces. And then HBK has a wide offering for end-of-line testing outside of back EMF, so I'll just touch on some of those elements and how we can leverage them doing back EMF tests. So, end-of-line testing for electric powertrain. First of all, what is production testing? Many of you might know, but for those of you who are more traditional HBM customers, you may be coming from the R&D side and be having some new experiences in production. There's definite differences, and in production, we need really robust measurements that are going to be reliable and executable, 10,000 times in a day, or 1,000 times a day, or 100, whatever your number is. We're not necessarily looking for deep engineering insight, but we are looking to decide if a part passes or fails and possibly store data for quality, again, possibly thousands of times a day. But we need to take data and then make decisions upon it. We want to do root cause analysis for product defects. So maybe you want to understand if machine C on line 6 is having defects, or the raw materials coming from supplier A are having problems as you come through the line, or wear and tear issues. Kind of these big data things. We want to figure out why our parts are failing, increase throughput. Communication with the production line control, I think that's pretty straightforward. And then a results database, somewhere where you can store production statistics, store production monitoring, so managers can view data in real time, look at throughput. So a couple of the differences, but a lot of the same parts. In the electric powertrain, there's a variety of components. There's batteries, inverters, electric machines, gearboxes, transmissions. I think if we're sitting in here, we've probably all had some experience with one of these components or another. Our product portfolio does touch on battery testing for end of line, does touch on inverter testing for end of line, does touch on machine testing for end of line. We look at powers, things like noise and vibration, absolutely touches on gearboxes and transmissions. We also handle all these things in the R&D setting, but today we are going to focus on stator construction, rotor construction, and magnetic strength for the end of line tests. So if there's any questions on any of the other elements, we'd be happy to have that conversation, but we're going to talk mainly about magnet strength today. So permanent magnet rotor construction and potential sources of failure. So just a little background on motor construction. To start, a stator is made up of a series of laminations, so these thin slices of steel that are electrically isolated and then pressed or stacked together. These are then wound with a number of turns of conductor. This, for example, is a three-phase machine, so we end up with 6 windings. These can be bobbin wound, potentially machine wound, but any way you spin it, that there is a copper being turned around a post. These connections are then soldered together. Sensors are potentially inserted. Housings like this black plastic are potentially inserted. There's a lot of construction going on. Then we come to the rotor. The rotor, again, largely laminations pressed together, so these thin chunks of steel pressed together for the length of the rotor stack. Shaft is inserted, or maybe the laminations are placed around the shaft. And then the permanent magnets are pressed in. And I don't know, I don't like the blue. I gotta switch back to it. I don't know how much everybody here knows about permanent magnets, but they're not born magnets. When you mix your nickel, iron, and boron together, or neodymium iron and boron together, you don't get a magnetized chunk of metal. You get a chunk of metal, and then you need to pulse it with a magnetic field in order to make it have magnetic strength. So when we're assembling our rotor, we can either have pre-magnetized magnets, where when the magnet was formed, we pulse the magnetic field at it, it's a magnet, and then we insert it into the magnet slot, or we can put the metal in, so we can put the non-magnetized magnet into the slot, and then pulse magnetic field at it from the outside world. That being said, either way you execute that, there's a potential to either over-magnetize or under-magnetize those magnets. There's also a chance you could magnetize them with the wrong polarity. So there are things that can go wrong with inserting these magnets or magnetizing them. When we insert these sensors, we can have issues with position sensors functioning. We'll talk more about that. Or position sensors being misaligned. We can talk more about that. But there can be sensor failures. There could be incorrect wiring or bad wiring harnesses. There could be poor solder joints. So there's a lot of things that could potentially go wrong in the assembly of these seemingly simple things. But fortunately, these tests or these issues I mentioned here can all be covered with one rotational back EMF test. So you can really look at a large number of the functionality of these problems with one simple test. I think that's pretty exciting, and that's really the theme of the presentation today, what you're all here to learn about. Just in case you guys cared, the first job I had was checking the stator resistance between these 3 phases and building up some clever logic to make sure that all the phases were wound correctly. But that's a topic for another day. So back EMF and KE, what are these values? Why are we talking about them? So back EMF is kind of one of these fundamental physics phenomena, and it is denoted with Greek letter epsilon. And what we'll see is that in my little equation here, those of you who've seen my presentations know I don't particularly care for equations, but I think these are simple and meaningful. We have N, so the number of turns of wire, this is the number of coils in our stator, times d phi dt, phi being the magnetic flux. And really what this is telling us is that in my animation on the right, where I have a north magnet and a south magnet, as this rotor spins by a coil of wire, this rotor has a value of flux, magnetic flux. And as it's spinning by that coil, if we remember back to our calculus courses, d phi dt is the change in flux over a change in time. So as this magnet is rotating by that coil, the flux field apparent to the coil is changing over time as it spins. So when we have this number of turns with this magnet spinning by it, we get this change in flux over a change in time, and we get this back EMF E that we have denoted here. And this is effectively just a voltage. Fancy name for voltage. So we get this voltage output. And the faster we spin this magnet, the more voltage we get. d phi dt is a shorter change in time, so that little t gets smaller, our back EMF or our voltage goes up. So nothing magic there. Now, I've introduced this back EMF or a back EMF constant Ke. It's really a function of machine. So when the machine is born, it has a Ke value. And this Ke value is really just the peak voltage, so that peak value from epsilon over the speed of the motor. So we take V peak over the no load speed, and this gives us our machine constant, our back EMF constant. And the reason we do this rather than just taking V peak is that if we were just to take V peak, we would need a very constant speed, and maybe our assembly line can't provide that. But with a relatively stable speed, we can get a good value. So by taking voltage as a function of speed, we can really understand this Ke value and use it as a term to decide if a machine winding or a machine magnet is good or bad. And really, the point I'm trying to get at is if a magnet is moved by a coil of wire, it will create a voltage proportionate to speed, and we call that Ke. All right, now we're all experts in motor physics, so let's move on to position sensors and why we care about those. So in every permanent magnet machine, which is what we're here to talk about, we're going to have a position sensor, and this position sensor can be used both for position, and then we can get speed from that by taking the derivative. And really what we're looking for is where is that rotor in the rotation of our machine? And this graphic on the right here is just a machine spinning around its axis, nothing magic there. And the trick is that in permanent magnet motors, we require the position sensor 0. So let's say this is my position sensor up here, and we know this to be 0. We want that to be lined up with our magnetic 0. And when I say magnetic 0, what I mean is where the peak magnet field is in terms of the magnet. And when we align magnetic 0 with position sensor 0, we're going to get the best machine operation, or we're going to get the highest torque per amp, or we're going to get the best efficiency, or in some cases, we're going to get functionality. Whereas if that peak magnetic 0 and that peak position sensor 0 aren't aligned, we might have derated torque, derated efficiency, or a non-functioning machine. So it's really important that we align these two things and that we have a position sensor. Now, position sensors come in all shapes and colors and flavors. A couple of notable ones are Hall effect sensors. These are the ones we'll be discussing today. We'll have optical encoders, which are really 2 pulse trains with a reference pulse for position. And then resolvers, which are a sine cosine. But what all of these sensors have in common is that they all require external excitation, and they all need to be aligned to magnetic 0. So we want that position sensor 0, or position sensor north, some might call it, aligned with peak magnetic flux. So back EMF test. What does this look like? Now we know what back EMF is. And it's really, in theory, fairly simple, and the devil's always in the details. But we have a stator with a known number of turns and an open circuit, which I have displayed with this kind of stator with the 6 windings on it in my graphic on the right, and then that's brought out to the 3 phases in the neutral. We need excitation for our position sensors. We need the load machine to spin this at a known speed. So we need a test rig that can spin this at a known speed. We need data acquisition equipment, which is where we come in to measure these voltage and position signals. And then the real magic is we need software logic to make decisions based on that data and really do some computations to get to pass or fail. And I really think this graphic on the right sums what we're accomplishing in a physics sense really, really nicely. We have windings with a number of coils. We have a magnet spinning about its axis. And as that magnet spins by that coil, we can watch voltage produced. And that's really our back EMF. So what does this look like in a block diagram? I love block diagrams. So we have an assembly line, and that assembly line's got a test stand with an inverter and a drive motor. This is going to spin up our machine. We have a rotor under test. This is either going to be placed into the assembly line fixture by an employee, by a technician, by a robot, whatever your assembly line calls for. It's then going to be inserted into. Now, in this example, the test stator is part of the whole assembly line, but in theory, it could be the production stator, and you could do this test once the rotor's been inserted as well. Kind of a fielder's choice on that one. But in this example, we will call it a test stator or a golden stator, something that's really had this no number of turns. We know it's good. So we're going to insert that rotor. We're going to measure, and this is a HBM Genesis eDrive system. So this is our measurement equipment. We're going to take those three-phase voltages, measure those. We're going to take position sensors. We're going to measure those. And we're evaluating the strength of the permanent magnets. We're going to spin this rotor up to a known speed. The acquisition hardware is going to take a very fast measurement. We're going to acquire that data. And then an automation PC is going to make a decision, pass, fail, and we're going to send that information back to an assembly line, back to a decision-making process, back to a technician or a worker who can decide if this rotor goes in the pass bin or the fail bin. I'll quickly introduce our product. This is our HBM eDrive system. It comes in a couple of different flavors and sizes to fit all of your company's needs. But one of the things we do particularly well is we measure electric and mechanical signals. So we can bring in your three-phase voltages. If you want to look at currents, we could bring those in. Bring your position sensors in, bring in accelerometers, load cells, force sensors, torque sensors. Really a wide variety of sensors can be brought into this system. And while we're talking about back EMF today, this really helps you future-proof your testing capabilities. Because if today you're testing a three-phase machine, you're good to go. But maybe tomorrow you have a six-phase machine and you need to expand out. Well, we could just add another acquisition card, and you go from 3 phases to 6 phases. Or maybe you want to bring in vibration measurements or a force sensor, or pick your favorite end-of-line test measurement. We could add a card, and it's a simple update to your cell. So we really like to think we future-proof your system. We have a really nice off-the-shelf software. So we have really nice visualization tools, automation tools, and then feedback tools. So we can give you a really nice user display of what you're looking at, and we can give you equations to automation systems. It's really nice and easy for setup. Our testing is auditable, and what that means is that we record all the data. So when you do a test, we don't just give you a result, we give you all the data behind it, and you can send it to the cloud, you can delete it, you can do whatever you please with it, but it's all there for your needs, and you can start making decisions about upstream things. We can start seeing trends and understand upstream problems. And lastly, we make our equations editable. So if you want to run a test in a certain way and you want to change your tolerances, you can go in there, make the change the tolerances. You have complete transparency to the data and to the test and to the equations that are operating that. So our big thing is transparency. So that's our product, and the tests that I will show in a moment are going to feature this product. So back EMF test example. Let's get to the fun stuff. So unfortunately, a lot of you guys out in the world, a lot of you customers won't give me machines to play with, so I had to find my own. And I very successfully found a permanent magnet motor. So I took a certain appliance apart, and I got a three-phase rotor, or a three-phase stator, and this happened to feature a permanent magnet rotor. This particular permanent magnet rotor has 4 magnets embedded in it. It has Hall effect sensors sitting on the rotor, so there's a little circuit board here that requires excitation. And we're going to evaluate how strong these magnets are and if they fit our needs. This test rotor with the pre-magnetized magnets is going to be inserted into the stator housing. We're going to spin at a fixed speed. We're going to measure voltage and position, and then we're going to apply some equations and make decisions. So pretty cut and dry. Let's look at some more detail. Now after the acquisition is really when the magic happens. So for a given machine, you need to know your tolerances. You need to know tolerances for KE, for angle offset. How much deviation from magnetic zero can my position sensor be? You need to know frequency. Maybe you need to know voltage levels. Then we run the test. So we set the tolerances. We run the test. We acquire the data. From here, we look at our signal levels. Are signal levels okay? Did the technician hook up everything? Do we maybe need to rerun the test? We determine the electrical frequency, so we need to know what speed we're at. Speed, if we remember, is a part of KE. We're going to calculate KE for each phase, make sure each magnet is magnetized correctly. We're going to calculate the angle between the position sensors and the magnets, make sure that's okay. We're going to check the polarity of the signals, make sure our wiring harnesses are correct, our sensors are installed correctly, our magnets are of the right polarity. And then, based on all of these, we're going to make a pass-fail decision. And again, devil's always in the details, but these are things that we can implement through our eDrive software. So on the right-hand side here, I just have a quick snippet of some of the equations I used for this given test. There's a whole lot here, but this was just a quick version of some of the KE values. And everybody's setup's going to be unique. Everybody's tolerances are going to be unique. Everybody's position sensors are going to be unique. But one of the big things is we make all our equations viewable and editable. So even as your suppliers change, as your test changes, you can make these updates on the fly. You can add extra calculations. You can add things that are specific to your needs. You can get really cute and maybe do a harmonic analysis on your signal if you want to look at harmonic content of it to make sure it's correct. You can get clever. But you have all the equations. Another thing is, because we store all the data, you can take this software and take it to your desk. And if you have a new rotor, you can run a couple runs on the new rotor, bring all that data back to your desk, open up the software, and run all these tests in the post-process. And what that allows you to do is, using the same software, the same set of equations, and the same data, tune your tolerances, understand failures, do quality control. So you can do one test out at the stand and then go back to your desk, go back to your office, and figure out how to remake your test or how to update your test for your new rotor, for your new stator, for an issue you're having. So you have absolute control over your test stand. And I think that's a really powerful message, just based on some of the feedback I've gotten from a couple of our customers around the world. So test execution. As we mentioned, we're going to hook up those three phases to the test equipment. We're going to hook up those position sensors to the test equipment. We're going to place the rotor in the stator. We're going to put that guy in there. We're going to spin up to a known speed. We're going to take a very fast measurement, 0.1 seconds in this instance. We're going to pass data through analysis. We're going to get a pass-fail output, and we're going to archive that failure data for whoever wants it. And we're going to get a little pass on our computer screen here, and we're going to move on to the next test. So with that, we run this test. Let's look at an example of a pass. So we'll start out with a good test, and then we'll look at the fun ones. So firstly, in the right-hand side here, I've got a little breakout display with my angle values for my three phases. I've got my KE values for my three phases. I've got my limits for my KE. I've got a value I call polarity, and then I've got my speed, which in this case is 16, 19 RPM. So let's look at our KE. Our KE, if we remember, is peak voltage over no load speed. So we spin it up and we see our three-phase voltages in the red, blue, and maroon. And these have, this the sinusoidal function to it with a little harmonic from the magnet. But these are what we expect to see. We've got a really nice amplitude at 1.5 volts. Frequencies as expected. This is beautiful. We get that V peak taken here. We divide by the speed, and we get our KD value. We also have this position sensor. This position sensor is shown by this black square wave here. And this is my Hall effect sensor just firing periodically. And this one's a little more complicated. This is actually the fun one. So we want to look at the distance from the zero crossings of the three phases from both the rising and falling edge of our Hall effect sensor. So I tried to detail here. The falling edge is my hard black line. That's the falling edge of my Hall effect sensor. And I'll just write that down here. And the way we're going to determine if the angle is correct is we're going to take that falling edge of the Hall effect sensor, and we're going to look at the time between that falling edge and phase A zero crossing. The zero crossings are an easy thing for us to measure. So we take that time and we translate that through speed to angle. And here we get an angle. We'll call that angle 1. We also look at the angle in maroon between the falling edge and phase 2 zero crossing. We're going to call that angle 2. And then naturally the blue is going to be angle 3. And from that, we can make a decision whether these angles are good or bad. So a little computationally cleverness involved, but not too bad. So we can take those distances and we can take those times, translate them to angle, and figure out if it's pass or fail. And then what I found was with this particular sensor, if we were rotating backwards or if we were flipped the polarity of the voltage, the speed signal, so the Hall effect sensor signal messed up. So I needed to put a little check in there for polarity. So we wanted to see if the sensor was wired correctly or if I was spinning the test in the right direction. So we look at those three things and we get a pass test. But passes, we pass. What's interesting is when things go wrong. So let's look at a few failed scenarios. Scenario 1, we spin up our machine. We got a good RPM. But what we see here is that my position sensor value is just flat. Well, what we found out was that the position sensor wasn't working. We got NAN, no value available. Well, the failure was lack of sensor excitation. The wiring harness was messed up in this particular scenario. We weren't able to measure position. So that failed. So we have information on why it failed, as well as the data to show us why it failed. So these are things that we can feed back to quality control. Next scenario, if we look at this KE value over here on the left, this is a pass. So we had a good amplitude. Well, on the right-hand side, we're still at 1600 or 1620 RPM, but our value is, roughly half. Well, our KE is too small. These magnets likely were not magnetized correctly. So that's potential failure we would see. Or maybe one of these phases was off. That could be a failure we see. But this is going to indicate to us that KE is too small, our speed is okay, we're likely not magnetized correctly. But our position passes, our angle passes, our polarity passes, but our magnets are no good. Lastly, this one looks like everything passes. We've got good speed, we've got good amplitude. This position sensor looks okay. What we found is we failed on polarity because in this particular test, the test was spinning backwards, and we got a polarity failure. But it could also be indicative of the sensor being installed the wrong direction. It could be indicative of poor excitation or incorrect excitation, incorrect wiring harness. And again, for all these scenarios, we record all the data that can all be sent to the cloud or sent to quality control or used by R&D to determine tolerances or potential failures. So some really cool stuff here. And I think understanding failures is probably as important or maybe more important than understanding passes. One other scenario I just wanted to look at before we move to the really exciting stuff is here's an example of a test where rather than spinning at 1600 RPM, we were only spinning at 1084 RPM. But we see we still got a pass. Because KE is ratiometric, because it's V over omega, and as V goes down, omega goes down, we can really have some flexibility in this test. So as long as you can hold a somewhat constant speed, you can get a good measurement, and that gives us flexibility. Rather than just looking at a very specific peak value, we can start to understand across a wider range of speed values. Our position sensors are still going to work. The polarity is still going to work. So this gives the test rig some flexibility by looking at KE. The problem with this is that this method might struggle at very low speed. And when I say low speed, I mean kind of like flick of the wrist or speeding up or slowing down, so variable speed. This might run into some issues. And while this might not affect people who have really high-end test systems, where this might affect people is the lower budget side of the spectrum. Maybe you're doing 5 or 10 machines a week, and you don't have the budget to have a high-end test system. So you have a method of spinning the rotor to check this, but you don't necessarily have full-blown automation equipment. This might be a difficult method for you. And you might say, Mitch, you're trying to sell me equipment at some level. Why are you telling me this? Well, I have a wonderful advanced back EMF test for people who might not be able to hold a constant speed or might have to do a variable speed test. So another way we can look at back EMF constant is by determining magnetic flux. And magnetic flux is just a measurement of magnet strength. So we're no longer looking at the machine constant, we're looking at just the pure magnet strength. So we can determine magnetic flux, lambda, with voltages. And again, magnetic flux, measurement of magnetic strength. We can use it in the same way we use KE to tell if how strong the magnets are. But the beautiful thing is this calculation can be made without a fixed speed. We no longer need to have a static speed value. And what we're going to find is we no longer need it to be at a certain threshold. So this allows for very flexible test rigs. And what we can see is that we have a whole new set of equations, and there's some really fun math in here. And we use some a little more complex math to get to some outcomes. I won't belabor the point. I just wanted to put in that this is a flexible system where you can update equations and you can make changes and you can see exactly how it's all being done. So let's run our first test where we're looking at magnetic flux. So being the scientist I am, or think I am, I wanted to start with the same baseline. So let's run the exact same 0.1 second test that we did in the previous section. Let's run it at 1600 RPM and see what kind of values you get. So we're still going to measure the position sensors. And what we get is we get our three-phase voltages. And we see we have our three phases here. We've got our position sensor value, nothing too exciting here. I don't really use it. I just put it there as a reference for speed. What we see is we get this kind of integrator wind up, and then we get this constant value. And then we get this integrator fall down. But we get this nice constant value, and it's 2.23 millivolts seconds. Okay, we get a value for a static test. We're going to call this the kind of golden value. We know it worked for KE, so we assume it works here. Next test, we go from 0 speed up to 1600 RPM, back down to 0 speed. So we're constantly changing frequency in this test. What we see is we get our integrator wind up, just like we had on the left-hand side. We get this constant value, even though our speed is constantly changing. Now we get this integrator fall down. So this is looking really familiar. And we get 2.26 millivolt seconds. Well, this is pretty cool, but I still spun up to 1600 RPM. And if you're proposing that this could be used maybe in place of some more sophisticated equipment, well, I've got a fun message for you. So on this particular machine, I is going to simulate a kind of less elaborate test stand or maybe even a hand-spun test by spinning the rotor by hand. If I can spin by hand, I think it will work in pretty much any scenario. So my test on the left, I just took the rotor and I gave it a quick spin. And we can see we get this little envelope here where it speeds up and slows down, and I am at a constantly changing speed, and I am not going all that fast. If we look, this is about a 1 second or second and a half test. And we can see we got the exact same scenario. Integrator wind up, constant value, integrator spool down. And we get 2.27 millivolt seconds. This is really cool. This is a hand-spun test, and we're getting almost the same value. So I just wanted to validate. I wanted to take it a step further, and I took the test. I took the unit under test, and I just spun it by hand a whole bunch of times. And what was really cool is I've got this little guy here. You see all of these have a certain amplitude from that hand-spun test. This one I must have just had a weak wrist on, and it didn't spin that many times. It's got a short amplitude. But if I look at my lambda, I look at my magnetic flux, I still get a valid value. I get 2.258 millivolt seconds. And if we compare those four tests, 2.36, 2.26, 2.27, 2.25, these are all really within a margin of error. These are within a tolerance value. We can use this test to determine if our magnets are strong enough. This is really exciting stuff. And again, this is really powerful. The downside is if you want to have more data on upstream topics, you don't have a fixed speed, so you have another variable. So if you want to understand more about, is production line 5 the problem I have, you might not have as much information. You'll still know if your magnets are good. You might just not know why, because you have another variable in speed. But really powerful for people who might not have the throughput or the budget to have that high-end test equipment. So, quality control and audits. I promised it, and I think it's a really important topic. So, because we record all that data, like I showed in those previous tests, you can store it all, you can save it, you can delete it, you can send it to the cloud, but all that data is there and all those equations are there. Quality control groups have that transparency. Assembly line tolerances can be adjusted, and you can start to get a big data thing and really have an industrial Internet of Things. And HBK does have big data solutions, and I'll touch on some of those a little bit. I'm admittedly not the best expert at it, but we absolutely have people who know a lot more than I do, and I'd be happy to point you in their direction. I just want to really belabor the point that we can do it, and I do have a nice example in a couple slides. And in this test, we get a fail, send that data to the cloud. Custom GUI and workflows, I think this is pretty cool. For certain customers, they've requested some specific things, and we've implemented them. One of them is having an operator login. We want to know who is running the test, so they log in. Or you can log in as an administrator and change values. We had another one that I thought was really cool. They wanted to have a barcode on their machine. Scan the barcode, and we set up the KE values for you. So we give you the machine name, the serial number, and you can really trace the test. But for our purposes, we're really setting up those tolerance values for that machine type. We can give you a little user display. If you have a technician hand mounting this, we can tell you for that machine type that we got from part 2, where to make the connections. And then when you actually go to run the test, we can say, we're a little in the gray area. Let's rerun that test. Or no, this thing definitely fails. Or yes, it passes. Move on to the next station. So some really cool stuff that we could make available to you. Other test offerings from HBK. There's a division within HBK called Discom, and we have some really cool products in that area. This division was founded in 1995 and is really focused on understanding rotating machinery and the art of failure in assembly lines. So their whole thing is production machinery and understanding when failures happen and how failures happen, mostly using noise, vibration, and electrical measurements to understand manufacturing flaws. And it's amazing the level that we can determine failures. We can tell you which gear tooth has a chip in it. and then start to use those types of things from this frequency spectrum to understand, did that come from assembly line A, and much more detailed things than I understand. We have a really complete solution in that space. So we have sensors designed for production. We have front ends that are user friendly. And then we have a comprehensive suite of data analysis tools. And that's really where the tie-in with back EMF testing comes in. And on the right-hand side here, what this is we have a blue tolerance graph, and then we have a spectral plot in green. And if that green line exceeds that blue line, we're in trouble, and this might not be a pass. We do a lot of work with electric machines and not just the back EMF in this area. So we can use, again, spectrum and order plots to look at orders, to understand imbalance in bearings, understand shaft imbalance, understand broken rotor bars, or use it to understand unbalanced magnetic fields. And I think that unbalanced magnetic fields is really where we tie in with the back EMF. Because back EMF could either be a leading or a lagging indicator in the assembly line of something going wrong. And we can start to use that data and understand more from a big data perspective how these things result maybe in failures down the line. So our magnetic strength might pass, but maybe the shape of the magnet isn't quite right, and that results in a magnetic unbalance in the final assembly. So then we can take that final assembly data and say, all right, we need to understand the harmonic content of that back EMF, and we can start to get better testing earlier by combining these data sets and understanding things collectively. So there's some really cool stuff here, but really where the immediate value add is for anybody doing back EMF testing is through the big data. There's a whole software suite really designed for giving feedback to managers, giving feedback to the higher end test system, and identifying leading failure indicators. So we have a few displays shown on the screen here. Display one could be local production statistics. At a given line, we're looking at, what's the failure rate for reason X and in that particular station. We can then move from a particular station out to a larger view. All right, in a pie graph, how many passes am I having? How many failures am I having? And what is the reason behind those failures? In this pie chart here, I believe we have different reasons of failure broken out in the pie segments. And then the really cool thing, in my opinion, is we can go even a step further and start doing some statistical analysis. Let's understand, if we have a bell curve of our tolerances, what's passing, what's failing, and then with really high certainty, we can go out a couple standard deviations and say, all right, we've got 5 millivolt seconds. That is way outside of 2 standard deviations. This is an obvious failure. We don't need to rerun this. Looking at reason behind failure, leading indicators of failure, and understanding how to adjust our tolerances, and a whole lot of things that are honestly outside of my area of expertise. But I think this is really cool stuff for adding value to your test stand and understanding things up the line. So my conclusion, the eDrive test system is a fast and flexible way to measure back EMF. Back EMF test stands can easily evaluate position sensors as well, so we can kill 2 birds with 1 stone. Advanced eDrive equations allow for flexible test stands, and we really give you complete transparency so you can own your test. You don't need to call somebody in every time you want to make a change. Data storage allows for quality control and traceability, and HBK has a broad offering of end-of-line test equipment and a lot of experts on board. So with that, I'd like to let everybody know that if you pull out your phones and scan these little QR codes here, you can ask me questions direct on LinkedIn. Or if you want to learn more about our products, you can scan this code on the right-hand side. Otherwise, Krista, I think I will open it up to you for questions.
All right, Mitch, thanks. Everyone, I will share Mitch's presentation with you, everyone who's here today. You should receive that today or tomorrow. We also record these sessions, and you will be notified when the recording is available for on-demand viewing in case you want to go back and review a point or share the information with a colleague. As Mitch said, we've got time for some questions. So if you want to type a question into the Q&A feature of WebEx, just be sure you share that with both the host and the presenter so we can respond. All right, Mitch, what do you mean when you say magnetic zero and position zero?
Yeah, good question. That's kind of an abstract thing to get your head around the first time. So if we took this, you know what, I'll do a little erasing here. If we took our rotor, our nice round rotor, and we have a magnet here, and a magnet here, magnet here, and a magnet here, and let's say this is north, our position sensor is going to tell us where we are if this machine is rotating. So if we took this machine and we flattened it out and we looked at it magnetically, we'd have magnet 1, magnet 2, magnet 3, magnet 4. In our position sensor, we really want position 0 to line up with magnetic 0. So if this is my peak north, I want my position sensor to say, all right, every time I'm at the top of rotation, peak north is also at the top of rotation. So we want that position sensor to have its 0 pulse here. Now, if that 0 pulse is somewhere out here and it's not at the peak, we might have a derated torque, we might have a derated efficiency, or we might not have a machine that functions. So it's kind of an important thing just for making sure we get that permanent magnet machine operating correctly.
All right. Why would I want to use accelerated testing rather than a traditional test?
Yeah, I think the accelerated testing, or the measuring lambda instead of the KE, is again really useful for the people who might not have access to really elaborate test stands. You could absolutely do that test with a fixed speed test rig as well. I think that's a cool way to go. I'm sure people have various reasons for doing various things, but I think the main reason that you would maybe do the accelerated test is that you didn't have access to a constant speed source. So it might be budget friendly. It might just fit your test profile. Maybe you want to run a NVH ramp sweep and take back EMF at the same time. It might appeal to both worlds.
All right. Well, everyone, thank you again for joining us today. And Mitch, thanks for an interesting presentation. We hope you all enjoy the rest of your day.